This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs. Also, make sure to check out and subscribe to our YouTube original channel, UCTV Prime, available only on YouTube.
Good morning. I'm Kelly Bauers, the Superintendent of Schools for the Livermore Valley Joint Unified School District. Very pleased to be here today and very honored. The focus of our school district is to inform, inspire, include, and innovate. And today, as a result of the efforts of the Lawrence Livermore National Laboratory, you will be informed, you will leave inspired, you're definitely all included, and you will see the highest level of innovation. So welcome to Livermore and the beautiful Bankhead Theater, and to the last but not least of 4 Science on Saturday presentations for the year. Local educators, in conjunction with the Lawrence Livermore National Laboratory, produce these series so that you can learn science from those who are making history through its use. This year, we are broadcasting this event live online by visiting the Livermore Lab Facebook page, or you can even watch on your mobile device by visiting livestream.com/LLNL. Questions can be posed to the presenters with the chat box below the video player, or you can even tweet your questions by including Science on Saturday hashtag. The notes of this presentation can also be downloaded, and many of the students here will receive extra credit in your classrooms for participating today. So I'd like to start first by thanking Mr. Dick Farnsworth, who you met earlier, and his staff for producing the Science on Saturday series. Please give a big thank you also to the folks in the booth and the camera staff. Our lecture today is Restoring Sight to the Blind, Bridging the Medical Gap with Technology. And I'd like to start off with 2 quotes from Helen Keller. One is, of all the senses, sight must be the most delightful. And the other is, there is something worse than having no sight. It's being able to see, but have no vision. And the folks that you will hear from today who will be presenting will be sharing with you how they've made their vision for something that will help many folks in the world, how they made that vision come true. I wonder what Helen would have to say about today's subject. Millions of people worldwide suffer from ocular diseases causing blindness, and they're left with little hope of seeing. Today, the lecturers will explain about a device that may restore sight and how they have developed an artificial retina that can function in the harsh environment of the eye. So let's find out who these esteemed speakers are. I will start with the first introduction. Dr. Sat Panu is currently the section leader for the Center for Micro and Nanotechnology in the Engineering Directorate at Lawrence Livermore National Laboratory. His latest publication, Advanced Neural Interfaces, was released in April of last year. Dr. Panu began his education at Yuba Community College, and then he obtained his doctoral degree in mechanical engineering at UC Berkeley, my alma mater. We've already discussed this, go Bears. So please give him a warm welcome, and then he will introduce the other presenters. Dr. Panu.
Thank you, Connie. So, good morning and welcome to Science on Saturday. So we're always excited to get an opportunity to talk about our research, and today we'll be talking about technologies we use to restore sight to the blind. It's always fascinating to kind of think about how technology progresses over time and how we always move much more quickly with technology than we do with medical science. And today we'll underscore that point with talking about the retinal prosthesis, which is what the device is that restores sight to the blind patients. But of course, you can't all do this in a vacuum. I stand up here as one of the people that lead this project, but it's really a team effort. And I'd like to introduce my team before we get going. And so first up is actually Sarah Felix. She received her PhD in mechanical engineering from UC Berkeley. Her expertise is in MEMS, which is micro electromechanical systems. She's actually been at the laboratory now for 2 years, and she's been an integral part of our team for developing this retinal prosthesis. So let's thank her. And next up is Kedar Shah. He also received his degree from UC Berkeley. He received his master's in mechanical engineering. He joined the laboratory 3 years ago, and his expertise is in complex alignment and fabrication of little pieces, especially MEMS, micro technology sized devices. And he'll be talking more about our device and kind of how it functions. And next up is Hiral Seth. She received her master's in biomedical engineering from Michigan. She joined the team a couple years ago as well, and she's obviously an expert in biomedical devices, which this device qualifies. You'll see more about that later on. But understanding the biology and actually how it relates to our medical devices is really important, and she brings that expertise to our team. And next up is Vanessa Tolosa. She received her PhD from UCLA in chemical engineering, and she also brings expertise in understanding how neurons function, how they operate in the body, and how we can communicate with them in an electrical manner. And so let's thank her as well. And next up is Angela Tooker. She received her PhD from Caltech in electrical engineering, and she actually also received her undergraduate degree from MIT. And so she's got quite the pedigree and brings a lot of horsepower to our team. And so she's been with us for 3 years at least, and she brings a lot of expertise in the MEMS fabrication, so actually making these little micro devices. And so let's thank her as well. And of course, the whole purpose of this talk is to give you education on what's going on. And so Kirk Brown is a high school teacher at Tracy High. He's been there for quite some time, and is San Joaquin Teacher of the Year. And so we'd like to thank him as well for helping us get our presentation, and he'll have a great demo for you guys as well. So let's move on. So of course, you're all here today. We're going to teach you some lessons about the retinal prosthesis. And so the first question is, all these prosthetic devices, they actually have to interface with a neuron. So it's really important to understand how neurons work. And so the first part of the talk will actually give you guys an idea of how neurons work, how they function, how they communicate between your brain and your senses. And of course, the most important part is you are your neurons. And so as we're talking here, your neurons are changing to what we're going to be presenting to you. And that's something that most people don't understand. And so your memory is actually formed by all these networks of connections of your neurons. And so that's really important. And we'll actually describe how that function occurs. And of course, how the eye works, right? Before we can actually restore function, we actually understand how the eye works, how it actually forms images, how those images get interpreted in the brain. And of course, we'll talk about the principal components of the eye, and also talk about what can go wrong. And so in these cases, there's 2 diseases that we'll describe that actually rob people of their sight. And then lastly, we'll actually show you how we can actually restore sight, the function that's been robbed by these diseases, by actually implementing our technology. And so of course, what is a yeah, that's right, Darth Vader. So what is a neuroprosthetic device? So simply put, it's any device that actually interfaces or communicates with the human nervous system. And so that's actually a broad range of devices. It can be anything from something that restores function to your hands or to your legs, restores function to your auditory system or your visual system, or even actually interprets and restores partial function to your brain. And so the most famous example was actually Star Wars in the media. So the first Star Wars movie, actually I guess it was actually the second Star Wars movie, Luke Skywalker actually gets his hand chopped off, and actually they restore his hand at the end of the movie, and it's actually just like his actual hand, right? He has the fidelity of movement with his fingers. He actually has sense of touch. You can't tell the difference. And that is actually the neural prosthetic interfacing with his nerves, so the command of moving his hand actually goes to his fingers. The sense of touch actually goes back up through his nervous system to his brain. And so that is actually a great example of a neural prosthetic device. And then of course, in the previous movies, which actually came later in time, his father, Anakin Skywalker, gets damaged to the point where he loses all his limbs. And he is actually another great example of what neural prosthetics can do, at least in science fiction. They restored both his legs and both his arms, and he actually had full function. You couldn't tell the difference between his actual robotic self and his human self. And so that's actually another great example of what neuroprosthetics, at least in science fiction, have been envisioned to do. And of course, science fiction always leads the way. It's always interesting, if you look back in time, and so you guys all know, Star Trek's been remade, but you guys know who these two characters are, right? That's right. So feel free to shout it out. And so back in 1966, they had a little tiny device, and I'll play this here, and you know what that is. Well, it's Spock, but what is Captain Kirk doing? He's talking on his communicator, right? And so that was the first wireless device to communicate. At that time, in 1960, if you want to talk to your friends, you actually had to pick up a wired rotary telephone, right? So you actually picked up your phone, you dialed the number, and actually back in those days, most houses didn't actually have their own line. You actually had what was called a party line, so all your neighbors shared the same phone line. So actually you could pick up the phone and hear your neighbor's conversation, and you'd have to wait, right? Or you could actually, eavesdrop on them and see what's going on next door. So that was actually the state of the art in communications in the 60s. And then over time, or the next few decades, it progressed, to the point where in the 70s we had the push button phone, still wired. And then in the late 80s, early 90s, we actually ended up having a wireless telephone. So now you weren't tethered anymore, but you still had the device you're carrying wasn't tethered, but it was still tethered actually to the wall at some point. And then in the late 90s, early 2000s, we actually had the first cell phones. And now you're completely free to go wherever you want. You actually have that device with you at any moment in time. It's totally yours. And more important, the cell phone is actually much more powerful than what the creators of Star Trek envisioned with the communicator. It's not only a wireless communication device, it's also a very powerful computer, which you could then play obviously videos, television, music. It's your gateway to the internet. It basically is a very powerful device now, and that was about 40 years in that transition. And so the question is, right now, what I showed you earlier with Star Wars, that's kind of where they envision the retinal or neuroprosthetic devices should be. We'll be showing you where we are today and how we can actually make that future happen. And so as we start out the introduction, making a cell phone is really complicated. But it is really just one discipline, it's engineering. Neuroprosthetics cuts across a lot of different disciplines, including medicine and science. So you really need to have a deep understanding of these other fields to actually function and make these neuroprosthetics. Without the understanding of how the nervous system works, for example, you can't really make a device because you have no idea what you're doing. You don't know what the device is going to be interacting with. You don't know how to communicate with these neurons, and that's really important. And so as you move forward in your careers, you should really think about this as you go through college, high school and college. You really want to kind of understand all these different classes, biology, chemistry, engineering, physics, because later on, as you go into a workplace, it's going to be really important for you to really understand that whole broad picture versus when I went through school, it was easy enough to just be an engineer. And so it's really important. So again, pay attention to what we're saying up here, and you'll see all the different kind of fields that actually merge to actually make this neural prosthetic. And on that note, the neural prosthetics actually obviously have to interface with your neurons. And so the first thing you have to understand is how your neurons work. And so Dr. Vanessa Tolosa is going to be up next, and she's actually going to describe how they work and how they make us who we are.
So today, go back one more. Today we'll be talking about some of the gadgets we make at the lab called neural interfaces or neural prosthetics. And as Sat said, a neural interface or a neural prosthetic is a device that interfaces with your brain cells or nerves to help some people who've lost some of their abilities. For example, if someone lost an arm or a leg due to an accident, or someone may have lost their eyesight due to a disease, or some people may be suffering from a mental disorder because their brain cells are no longer properly communicating with each other. What all of these problems have in common is that they all affect the nervous system. Your nerves act like the wiring to your brain. They're constantly sending information back and forth to your brain from the different parts of your body and from your environment. For example, if you were to step on a tack, the pain nerves on your foot would send a signal up to your brain saying, "Ow, that hurt." And then your brain would process this information and send a signal back to your foot saying, "Pick up." And so that happens all very fast. You don't even have to think about it. So how do you think your brain and your foot talk to each other, and how did it do it so fast? Well, if you were to take your brain and put it under a microscope, you'll see that it's made up of many, many cells. And these cells are called neurons. And if you were to zoom in on a single neuron, you'd see something like this drawing here. So under the picture of the tin can telephone is a neuron. And on the left side of that drawing, you'll see the cell body, which holds the nucleus. From the cell body are branchy extensions called dendrites. The dendrites act like antennas, receiving signals from nearby cells or from the environment. These signals are then converted to an electrical signal, which is transmitted down the axon all the way to the end of the neuron called the axon terminal. At the terminal, the signal is converted briefly to a chemical signal, then to be transmitted to a neighboring cell or a muscle. It's then converted again back to an electrical signal, and this process happens again and again until it reaches its destination. So that's how a signal from your foot can go all the way to your brain and back, and it happens fast because it is largely an electrical signal. But you're not just a single neuron or a single nerve. In fact, in your brain alone, there are 100 or almost 100 billion neurons. And each of those 100 billion neurons has thousands and thousands of connections. So your brain is actually processing all kinds of things. It's processing every thought you have, every feeling you have, everything you do. It's even telling your body to do things you don't have to think about, like it's telling your body to breathe, or telling your heart to beat, or telling your heart to beat faster because you're speaking in front of a large crowd and you're on a stage. So let's go to YouTube and look at a video that illustrates this signaling between neurons. So those flashes of light represent the electrical signals that are being communicated between your neurons. And when that happens, we say that your neurons are firing. Your neurons are firing all the time, even when you're sleeping. And as you sit here today in the audience, your neurons are firing like crazy. You're getting all kinds of images from the stage. You're getting sound waves that your ears are picking up, and it's being made by my voice. All these signals are being sent to your brain or being processed. And in fact, every time you learn something new, or every time you bring up a memory, those acts actually physically change your brain. They cause your neurons to make brand new connections to nearby neurons. So if you think about it, the brain that you have when you walked into the theater today will look different from the brain you walk out of when you walk out of this theater. So I think you get the idea that there are a gazillion neural connections in our brain and just within our nervous systems. But sometimes they get damaged. But because we do have a lot of neurons and pathways, we can sometimes work around them. work around the damaged ones. And that's what we do. We make devices called neural interfaces, which we use to send electrical signals to those neurons that are still okay, bypassing the damaged ones. So we're going to go to YouTube again because we love YouTube, and we're going to show a video from a movie that was first made in 1931. You probably have not seen the movie, but you will recognize the characters. I'm already hearing some of you say. And if you know the movie, just shout it out.
It's alive. It's alive. It's alive. It's alive. It's alive.
So you guys know the movie or the character Frankenstein? Right, so even if today's the first day you've ever heard the words neural prosthetics or neural interface, you're actually already familiar with the concept. Frankenstein was, or the creature of Frankenstein, was brought back to life using a neural interface on his brain, which they applied a whole lot of electricity to because neurons, remember, communicate largely through electrical signals. So this is actually based on a true story. In the late 1700s, there was a scientist named Giovanni Aldini who would perform experiments in public. He would take dead bodies, place them on tables in the middle of the street, and apply electricity to the different parts of the body and make them move. So you can imagine the people standing around. I mean, if you saw this today, it would be kind of freaky. Well, rumor has it that Mary Shelley, who is the author of Frankenstein, was inspired by his experiments and wrote her novel. So we may not be actually reviving whole dead bodies, but what we can do with our devices is that we can help someone who's lost a limb, like an arm. We can help them hold things again. Or someone who's lost their vision, we can help them regain some of that vision back. And next, my colleagues will talk about how the eye works and how we help to develop the artificial retina device, which helps some people who have gone completely blind.
Thanks, Vanessa. Good morning. So we're going to talk a little bit about how the eye works, with a special emphasis on the neurons involved with vision. The human eye works somewhat like a camera. The camera has a lens to focus the image, it has an aperture to control the amount of light coming in, and it has either film or a sensor to record the image. The eye has similar components. So looking at this diagram, we'll start from the outside and work in. The protective outer wall, which is the white part that we see in the eye, is called the sclera. The cornea is another protective part that also does some of the focusing of the light as it enters the eye. The iris controls the size of the pupil, and this regulates the amount of light coming into the eye. Next, the lens fine-tunes the focus of the light, and the iris and the lens are controlled by tiny muscles that surround them. Inside the eye is the vitreous humor. This is a fluid that helps maintain the shape and the pressure of the eyeball. Light passes through the vitreous humor to the retina at the back of the eye. The retina is made up of layers of different kinds of cells, including neurons, and these detect light and color. The macula is a small spot on the retina, and this has high concentrations of certain types of these cells, and it gives us detailed information about the center of our vision. All the neurons come together in the optic nerve, and this travels out the back of the eye to the brain. Let's take a closer look at the neurons in the retina and the optic nerve. Light enters the eye and travels through all these layers of the retina, all the way to the outermost layer. This is where the light triggers an electrical signal, which travels back inwards through several layers of neuron cells. And these are different types of neurons that have different functions. They're the rod and cone cells, the bipolar cells, and the ganglion cells. And the ganglion cells connect to the optic nerve, which is seen on the left, and this relays the signal to a part of the brain called the visual cortex. Now, it's only when the signal finally reaches the brain that it's actually interpreted as an object or an image that we see. Before it gets to where the brain interprets it, it's just electrical signals. So now that we've described some of the parts of the eye, we have Kirk Brown and some of his students from Tracy High, and they're going to give a demonstration of a dissection of a cow's eye to show some of these important features.
I'd like to introduce two of my students that are helping me today. This is Faith Gerhardt, and this is Clifford Liu. And so we're going to show you the parts of a cow eye. So on the left-hand side here, Clifford's got an eye that has all of the attachments right after it's been removed out of a cow. And so one of the things that you see initially is its eyelids. You can show you the eyelids, okay? And so right inside your eyeball, if you put your finger there and touch, what you would be touching is your cornea. And so that surface on the outside. Now this eye has been preserved a little bit, so it made it a little bit milky. But in a fresh eye inside of an animal, it's crystal clear, so you wouldn't even see that. If you look on the outside, there's also in this particular eye, you can actually see there's a tear duct, a gland that generates tears right there, would be like in the corner of your eye, and it lubricates the outside of your eye and actually has enzymes and stuff in there that prevent infection from your eye and things like that. Also on the outside, you'll see there's muscles that attach at the top and the bottom and the right and the left, so the cow can lift his eye up, down, right, left. But in reality, they have fewer muscles than we do, so if you watch a cow move around, they have to move their head up and down to kind of help with their vision, not just, you can move your eyes in all dimensions, so they have a little bit different than us. If you look at the second eye, we've taken all that stuff on the outside off of the eye, and you can see the outer covering, and that's called the sclera. In your eye, when you look at someone, you see that white part of your eye, that's the sclera. And then if you turn the eye to the back, you can actually see the optic nerve coming directly out of the back of the eyeball, which is kind of cool. Now, on this next tray, Faith's going to show you, when we cut that eye open, you can take the front of the eye off, and what you do is what you see is the lens right in the inside, and that lens happens to be a yellowish color. Yours is crystal clear. That yellowish color is because it's in preservative. So that would be like you having a cataract, and a cataract makes that milky and you can't see through it as much. So as you get older, those turn lighter, and your mom and dad might ask you to turn the light up in the room because it's hard to see. So that's the reason for that. And around it, you see there's the iris, the part that opens and closes and lets more light in. Now if you look at the back part of the eye, the vitreous humor has been taken out, and I'll show you that in just a second, but you see that Faith is going to move around the retina in the back. There's a little layer, a very thin layer, that's the retina, and you can see as she pulls that off there, that's just sitting, so you're seeing through that. Now, if you look at the next eye, there's the retina has been kind of pulled away, and if she hold it real still and point it right toward the camera there so you can see it there, and you can see how the retina all moves back toward the optic nerve, and that goes right out of the back of the eyeball. Now, the only other thing, there's the optic nerve in the back, and then look at the inside, there's some vitreous humor, and you can see it looks like a clear jelly, and that's what fills your eyeball up and gives it shape. So I hope that you've enjoyed seeing what an eye looks like on the inside.
Thank you, Kirk, Faith, and Clifford. So now I'm going to describe a couple specific diseases that result in the loss of your vision when some of the neurons are damaged. So here's a picture of two little boys as someone with normal vision might see them. This is what someone might see if they have age-related macular degeneration, or AMD. As the name suggests, this disease destroys the function of the macula. And remember, the macula is a little spot on the retina that gives us information about the center of our vision. Now, you saw Faith pick up the retina. You see how it's kind of a layer that could be peeled off. So what happens is in AMD is some debris and bad tissue can build up underneath that layer and separate the macula from the back of the eye. So it no longer receives the signal that the light would trigger. AMD causes the center of the vision to become blurry and lost, and it can get worse and worse. This is what someone with retinitis pigmentosa, or RP, might see. In this disease, the rod and cone cells in the outer layer of the retina gradually die. Someone with RP may start off by having night blindness, and then it would advance to loss of peripheral vision, and maybe even total blindness. So I'm going to show you a quick video of what it might look like to have this disease. And as you're watching the video, imagine how frustrating it might be for someone with RP to go through their daily life. So they can barely see the whole picture of a person in front of them. It's hard to pick up important information. It would make it difficult to navigate their surroundings. So it is important to note that with both of these diseases, even though some of the outer layers of the retina are damaged, some of the other layers toward the inside, the bipolar cells, the ganglion cells, and the optic nerve are still healthy. So now Kedar is going to introduce how we can use technology to restore vision function to the eye, taking advantage of these healthy cells.
Thank you, Sarah. So before we jump into exactly how we're able to restore eyesight to the blind, I'm going to take a few seconds here to recap what we've seen so far. So Vanessa came and she introduced us to this concept of how any communication that's done in our body is done through electrical signals that are transmitted by our neurons. And she also showed us an example in science fiction and also what people have tried in reality in cases where they're able to artificially stimulate these neurons to be able to transmit electrical signals to them. Next up, we had Sarah and Kirk, and they talked about how the eye works, and specifically how the eye is able to convert light into electrical signals. And these electrical signals, once again, are able to be transported to the brain by our neurons through the optic nerve. We also learned that in certain diseases, we lose this ability to be able to convert light into electricity. So how exactly does this system work? Well, we know that in diseases like retinitis pigmentosa and age-related macular degeneration, we lose the ability to convert light into electricity, but we still do have quite a few healthy cells and neurons that can still transmit electrical signals. So the artificial retina system that we have built takes advantage of these healthy cells, and what we do is we implant a tiny array of electrodes onto the retina, and we artificially stimulate the cells, the ganglion cells in the eye, with individual electrical signals that are then transported into the brain through the optic nerve using the healthy neurons that are still left in the patient's eyes. So our system for the artificial retina consists of three main parts. There's a camera that sits on a pair of glasses that is worn by the patient. And you can see in the image on the left-hand side, it's a mannequin that has a pair of sunglasses, and there's a camera mounted on it. And this camera basically captures the images that are then transmitted to the eye and finally to the brain of the patient. The second part of the system that we have is the visual processing unit, which is, in other terms, just a computer. And this is the computer that actually is able to convert these images into both wireless power and data signals that are then transmitted into the implant. And finally, of course, we have the third part of the system, which is the actual implant that is placed inside the eye. And this is what receives the electrical signals and sends it to the retina. So let's take a closer look at what the actual implant looks like. The schematics that we have here show what the implant looks like. And this is one of the parts that Lawrence Livermore National Lab has developed in conjunction with Second Sight Medical Products, which is our commercial partner, and also in collaboration with a few other universities and national labs. So the artificial retina implant part consists of three main components again. The first part is an antenna that you can see in the right-hand side image here. And this antenna is able to accept the wireless power and data signals that are coming from the external device. These wireless power and data signals are then transmitted through the antenna into what's the second component of our implant, which is the electronics package, also pictured in the slide here. And this electronics package contains a computer chip and all of the electronics that are necessary to be able to convert this wireless power and data signal into the individual electrical impulses that are then stimulating the neurons in the eye. It's important to note here that this device doesn't have a battery built into it, that we are wirelessly transmitting the power into the device, and that's how we're able to keep this device running for an extended period of time in the patient without having to remove it or replace it. And finally, we have the electrode array, and this is the part that is attached to the retina, and it's able to take these individual electrical signals that are coming out of the electronics package, and the electrode array consists of many electrodes that are now attached to the retina, and these electrodes are able to transmit individual electrical signals to the retina, which are then transmitted into the brain and interpreted as an image. So in the image on the right-hand side, you can see what the whole implant looks like. And what you'll see is the two components, the antenna and the electrode array, sit on the outside of the eyeball, while the electrode array itself penetrates the eyeball and actually is placed onto the actual retina. So that's all the theory behind it, but here's proof that we've actually built a device, and this is what it looks like. So this is an image of the latest generation device that Lawrence Livermore National Lab helped build. And the part on the right-hand side, the circular part of it, is the electronics package that houses all the electronics. And extending out of this electronics package, you see the electrode array, and all the way on the left-hand side, you see the array of 240 electrodes. And these are the electrodes that actually are placed on the retina and can stimulate the healthy ganglion cells in the eye. So when we talk about the number of electrodes in pixels, what does that actually mean? I'm sure all of you are familiar with your cell phone cameras that boast of megapixels, and a megapixel is basically 1 million pixels. But what I just showed you on the previous slide is a device that has 240 electrodes, and the previous device that we had 60 electrodes. So what does this mean, and why is it so important for us to increase the number of pixels or electrodes to be able to restore vision to our patients? So in the next few set of slides, I'm going to cycle through a few images, and this is a few recognizable objects or people, and I'm going to demonstrate what it looks like with just a few pixels and how the more pixels we add, the more recognizable the object is. So when you take a look at this image up here, it's approximately 60 pixels, and it's really hard to be able to say what this might actually be. When you go to the 240 pixel version of this, or 240 electrode version of this, it starts to make a little bit sense, but it's still a little bit difficult to guess what this might be. As soon as we go to the 1,000 electrode version of it, I think a lot of you can probably see that this is a person. And when you go to the 10,000 pixel version of this, we all see that we're looking at Albert Einstein. The next image has 100,000 pixels, and finally 1 million pixels. And this is something that compares with an image that you might take with a camera, whether it's in your cell phone or digital camera. So now I want to put up a few slides here. I have two other demos, and these are objects or people, and I want you all to guess what these might be. And I'm going to cycle through them in order of increasing number of pixels or electrodes. Here's the first image with 60 pixels. Anyone have any guesses? I don't think I'm hearing it, so I'm going to jump to the 240 pixel version of it. Still a little blurry. That's 1,000 electrodes. I think all of you have it. And for those of you who don't have it yet, here's what it looks like with 10,000 pixels. 100,000 pixels. It's a zebra. 1 million pixels. And then this is the color image that we would actually see. I'm going to do another demo. Once again, feel free to shout out if you think you know what it is. This is the 60 pixel version. I don't think I'm hearing it yet. This is the 240 pixel version. And I think I hear the right answer from a lot of you. 1,000 electrodes. And at 10,000, it's pretty obvious that we're looking at our president, Barack Obama. And that's the final version and the color version. So you now have an understanding of how the artificial retina system works, and you know how we're artificially able to send signals, electrical signals to the eye that can then be interpreted by the brain as images. But all I've showed you is a device. Does it actually work? And what does it mean to be able to see 240 or 60 pixels? So I'm going to pass over the mic now to Angela Tucker, and she's going to show you what exactly we've been able to do with these devices implanted in humans with some demonstrations.
Thanks, Kedar. So as he said, as Kedar said, he's demonstrated that the different components of the artificial retina and in general how it works. And I'm here to tell you that it does actually work. Right now, it's implanted in 40 patients across the world. All of these patients are completely blind. They either have macular degeneration or retinitis pigmentosa, and it's progressed to the point that they cannot see anything anymore. And so, Kedar was talking about, number of electrodes. These only have, 60 electrodes. The newest generations only have 240. And you might say, well, is that good enough? Can I really see anything with that? And the answer is yes. With the artificial retina, you actually can. These patients have the freedom to navigate in unfamiliar environments. Blind people are typically very good about navigating around their homes, areas that they're very familiar with. But if you put them down in an unfamiliar environment, it becomes hard to navigate, hard to, move around with all the different people and get around them. But with this device, they actually can see that. So this first demo is actually going to show you, there's two versions. There's this first version where the device is turned off. With this particular device, you actually can turn it on and turn it off. So this is a blind person, and all we wanted to do is just walk down this white line. If you can imagine yourself, if we told you to walk down a white line, you'd say, oh, that's really simple. But if you're blind, that's virtually impossible. And the left side is actually going to show you what the camera is seeing. With the device turned off, you obviously don't see much because there's nothing to see. The camera's not recording anything. As you can see, she starts off really well on the line, and she just veers off. And she'll never make it back onto the line because she can't see it. And just keeps going further and further away. So in this particular device, in this demo, we've actually turned the device on. And on the left side again, you will see what the camera is recording and the electrical signals that it is sending to the retinal cells. And you can see that white line that she's trying to follow, which she can follow now, is kind of moving in and out of her field of view as her head is moving back and forth. And so she is actually able to see, to see well enough to walk down a white line. She can walk around in unfamiliar environments. So in addition to being able to just navigate, unfamiliar environments, this device is actually going to allow you to be able to read. We have two demos here of, this is essentially what the camera would record and send to the retinal cells as you're trying to read different letters. And we'd like you to try and guess what these letters are as you kind of pretend that this would be what you're seeing and see how well you really can read. That's good. It is the letter C. And the second one is a little bit harder. Okay, so not a little bit harder. Previous audience had a little more trouble with this one. But as you can see, it took, yes, that is Einstein now. That took a long time to just read a single letter. And if you imagine trying to read just an entire page, it would take you a week if that's how long it took you to read just one letter. But this brings up another point. These letters are very large. And if we make the letters smaller, so we bring them closer into the field of view, we can actually begin to see more of them. Kadar talked earlier about, pixelization. And, at 60 pixels, you couldn't distinguish Albert Einstein from the Golden Gate Bridge. But if you go to like 240 pixels, you were able to start to distinguish those different images. But what's equally important is actually the field of view that you can see. So you can imagine, this is a very high, high resolution. There are a lot of pixels for this, for this image of Einstein. And on the screen you can tell it's Einstein. But if all you could see was, an area the size of your thumbnail, you wouldn't be able to tell me that it was Albert Einstein. You'd be able to tell me, oh, it's something gray. And so it's important as part of this that you can also get a good field of view with your images. So like this particular image, you may or may not be able to tell me what this is, but this doesn't have a high degree of pixelization. There's a fair amount of pixels here, but the field of view is just so small you can't tell what it is. But as I make the field of view larger, you can start to tell me what this is. So I'm hearing triangle, and I'm hearing A, and I'm hearing Aztec something or other. But this is, in fact, the letter A. So, this brings up the idea that, in addition to increasing the number of pixels so you can really distinguish objects, you also need to make sure that, your field of view is right. So if your field of view is really small, even if you have a really high pixel count, you're not going to be able to tell what you're seeing. But patients with this device are, in fact, able to, they're able to read. And so as long as the letters are small enough within their field of view, they can read books that they formerly were not able to do. So this last video is actually, this is a patient in France who has this device, and you can see the device on his head. It just looks like a pair of sunglasses, and he's pointing out to his companion the location of these various posts, and there are 4 of them, and he can see those posts. And in fact, you can't tell this right here, but he actually can see that person walk by, and so he knew that there was a person walking by there. And actually, in the bottom left of this screen in a minute, you will see there's a discolored area of the ground. And he's pointing that out right now. And he can actually tell that that area of the ground is discolored and is a different pattern than the rest of the ground. So we've made a lot of progress with this device. And, people who couldn't see anything now, they have a lot more freedom to do things. They can move around. They can read. They can see where people are, but there's still a lot of progress that we need to make, a lot of progress that we need you guys to make. And with that, I'm going to turn it back to Sat, who's going to speak a little bit more about the future of this device and other neuroprosthetics.
And so we just showed you the state of the art of the retinal prosthetic devices. So what do the other devices look like? And so I kind of started off the beginning of the talk talking about Luke Skywalker and his hand. And so the video on the lower left-hand part of your screen shows you actually a gentleman who's actually opening and closing a prosthetic hand just by thinking about it. And so actually you can see he's right there, and actually this particular device is not wireless. It's actually, there's a neural interface implanted in his brain, and the wires from that interface are actually coming out from the top. If you look closely at the video, you can actually see the connector right there. So it's still fairly crude, but he is opening and closing that hand just by thinking about it. And of course, a lot of our warfighters returning from Iraq and Afghanistan have lost either an upper limb or a lower limb, and so we want to restore their function. And how do we do that? So the government has actually invested a lot of money in developing a hand that's much, much better, actually an arm with a hand that's much, much better than this one here. This one just opens and closes, still just a really simple motion. Here, this is actually the state of the art. It basically replicates the full function of a human hand and an arm. The issue is how to control it. She doesn't have a neural interface connected to her either a peripheral nervous system or a central nervous system. She's actually controlling this device by flexing muscles in her chest. So she's actually thinking about, raising her hand up, and she flexes her pectoral muscle, raises the arm up, she relaxes, it goes back down. you think it seems like you can actually have a pretty good way of controlling devices that way. The problem is there's just so many muscles, and also it's very unnatural. So when you want to grab something, thinking about flexing one of the muscles in your chest is not what you normally do. So it takes a lot of time to train these patients, and even after a lot of training, they just get tired, right? Because by the time you reach that age, you're just used to thinking about grabbing something, and it's very natural motion. Thinking about changing that muscle reflex to another muscle is really difficult to do. And of course, this last video here is my favorite. This gentleman here is playing video games just by thinking about it. You can notice he's not playing with the joystick. He's actually just thinking about playing Space Invaders. So he's moving the little spacecraft left and right, and he's firing just by thinking about it. So you can imagine you can play, you don't actually get up off the couch anymore. You can actually just sit back and play your video game just by thinking about it. In fact, you probably play multiple games, just dividing your time between different screens. And so as fast as you can think about it, it'll happen. So that's actually pretty cool. And then of course, back to the retinal prosthesis, where do we go from here? So back to the analogy of the communicator and the telephone, we're not quite at the communicator. We're still at the rotary telephone stage. So how do we get to the spot where, in Geordi in Star Trek, back to our Star Trek analogy, he actually has vision better than normal people, right? He can see the whole electromagnetic spectrum, not just visible light. He can see infrared, he can see radio waves, he can see everything. And so how do we go from what we have now to there? And so that's actually a great question, and I just play a little video here. And so this is what he sees, right? This is like a simulation of what Geordi would see. And so you can see he actually kind of sees everything. He sees heat, he sees infrared or ultraviolet, he sees visual spectrum. And so, we could do this with our current device. There's no reason why you couldn't replace the camera instead of just a visual a camera that's sensitive to the visual light spectrum. You can actually replace it with IR, so you can see at night. You could replace it with replace it with ultraviolet, so you can see other parts of the spectrum. You can see wireless signals, right? If you replace it with something that can detect radio waves. So it's actually pretty amazing the range of function we can now give these patients. But how do we get here? And so that's actually a great question, and that actually depends on you guys, right? Because we've gotten this far, and so to go farther in this is going to take probably another 20 to 30 years. And you guys are the next generation that's going to come in and actually develop these devices. So the question really remains to you, what is this going to look like 20 years from now? And so, think about that as you progress in your careers. I know it's really early to think about what this is going to be, but you never can start too early. If I had an opportunity to kind of see this kind of work initially, I probably would have changed part of my career. So you really want to kind of pay attention to this, because you really only get one shot to kind of go through college, and you're going to spend 4 to 8 years getting your PhD, and that's a long time to repeat if you decide you want to do something else. And so, of course, just to summarize what we've learned today, we went through initially, just told you how neurons work and how they function and communicate. And of course, you are your neurons and your rearrangement of your neurons in a network. And of course, how the eye works. It's very similar to a digital camera, has a lensing system, has photoreceptors that actually change light into electrical signals. And of course, it has diseases that can rob you of those functions. And then we showed you how we can restore that by putting an electrode array that functions similar to the photoreceptors. So thank you very much. I appreciate your guys' time. If you have any more questions, come up.